So welcome everybody to the seminar today by Pratik Rath, and he is known to the small audience that we have so far. So no introduction needed, and he already gave us a talk in the conference that we organized earlier. Today he is going to tell us about corrections to the JLMS formula coming from, I think, Replica wormholes. Okay, over to you, Pratik. You are muted, Pratik.
Well, the problem is I have like two sounds.
Oh, no, I can tell you how to solve the problem. So on your iPad, do something, just disconnect the audio completely. So that will stop the feedback. So you can just disable audio completely, disconnect audio completely. So now there will be no feedback. Yeah.
Okay, I think that, okay. Can you hear me now?
Yes.
Okay, sounds good. Okay, thanks a lot. Okay, sorry for the technical glitches. I'm very happy to give this presentation to you guys. And I'd like to talk about this particular paper that appeared recently with my collaborator, Jonah Kudler-Flamm. And it's sort of in a direction that I've been interested in of late. So I'd like to share these ideas with you and maybe talk about some of the future things that I'm thinking about. So let me start by motivating the problem that I'm interested in. Wait, sorry, one sec. Do I get rid of this? Okay, I guess it's fine. All right, so let me motivate the problem that I'm interested in. The JLMS formula is what? Sorry, are you seeing my screen on
maybe
Mac?
do the following. Don't share screen. You can share, you have to share a particular app, right? Or you can turn off the video in your iPad, or is the video on in your iPad or not?
No, it's off.
Off. So when I think there is something called screen recording, and then you can just share the particular application. Maybe I pause the recording also.
All right. Okay, so let me get started by motivating the problem at hand. The quantity that we're interested in looking at is the relative entropy. And the relative entropy is defined as follows. So if I have two density matrices, rho and sigma, then the relative entropy, which is this quantity, is defined as trace rho log rho minus trace rho log sigma. And the relative entropy is sort of a measure of distinguishability between states. So the relative entropy between rho and sigma tells you how different these two states are, or intuitively tells you how easy it is to distinguish these two states, how easily you can do measurements to tell that the state you have is sigma or rho. The relative entropy has been used a lot in quantum information context because it has this nice operational interpretation. And in the context of holography, the formula, the JLMS formula by these authors, was the first which really used this relative entropy and found a holographic formula that describes the relative entropy in this context, where what it says is that the relative entropy computed on the boundary. So let's say we have this setup where we have a subregion A, and its complementary region A bar. Then what the JLMS formula says is, if I take two bulk density matrices, rho and sigma, and I look at the reduced state on the region A, then the relative entropy between them is given by the relative entropy in the bulk computed between the two states rho and sigma on the region, which I've shaded here, which is the entanglement wedge. The entanglement wedge is defined by looking at the extremal surface gamma A that's anchored to the endpoints of A. And the region between this gamma A and A, which is this shaded region marked little a, is what's called the entanglement wedge. Over the last few years, people have understood that the region of the bulk that should be thought of as dual to the boundary region is this entanglement wedge. So naturally, this is a formula that one should expect, where the distinguishability of the states on region capital A is in one-to-one correspondence with the distinguishability of the states in the region little a.
Can I ask a trivial question?
Yeah, sure.
Where is the data of rho A and sigma A going?
So you could imagine something like this. So you could, the simplest context where we can think about this is, let's say you have a classical background, some fixed background, and you have two different quantum states living on this background, which we can call rho and sigma. These two different quantum states in the bulk will map to two different quantum states on the boundary. And you can ask about their distinguishability. So for simplicity, we could say there's a spin in this region, which is up in one state and down in the other state, or something like that. Okay. So this is at this point, we're being pretty abstract about what rho and sigma are. But just for concreteness, you could consider any two different QFT states in the bulk, which we can pick. And then the non-trivial statement is that the relative entropy computed on region capital A in the boundary is the same as the relative entropy of the region little a computed in the bulk. So it's some holographic proposal for the relative entropy. Now, this was proposed many years back, and ever since then, there's been a lot of refinements to this understanding. And in order to tell you about that, let me first motivate why this formula is true. And there's really two ways to understand why this formula is true. The first way to understand it is from a Euclidean path integral perspective. So the Euclidean path integral is what one typically uses to compute things like the entanglement entropy, or for example, for preparing different states. And for the entanglement entropy, there's a nice formula, which is called the Ryu-Takenagi formula, which was then generalized to include quantum corrections by FLM, these authors. And what it says is the following. It says that when you compute the entanglement entropy of a density matrix on the boundary in region A, it has two contributions. It has a classical contribution, which is just the area of the extremal surface divided by 4G, which is the Ryu-Takenagi formula. It's the analog of the Bekenstein-Hawking entropy. But it also has a correction that is a quantum correction, that is the entropy of the entanglement wedge. So it's the bulk entropy computed on the region little a. This is what the FLM formula says. Now, you can take this formula and consider perturbations of the state. So you start with some density matrix rho and perturb it to, say, rho plus some delta rho, where delta rho can be an arbitrary perturbation to the state. When you consider arbitrary such perturbations, what you essentially find by using, by a simple perturbation theory on this formula, is that there's actually an operator equation. So there's an operator equation that relates the boundary modular Hamiltonian, where the modular Hamiltonian K is defined as minus log of the density matrix. So some function of the density matrix is given by the bulk modular Hamiltonian plus an area contribution. This is just, you can think of this as just some operator generalization of this formula. when you compute the expectation value of this in the state rho, you end up with the FLM formula. In particular, yeah, sorry.
I have a small question about this.
Yes,
So this operator equation, I've always had a doubt about it. That this it's on one side we have operators acting on the boundary Hilbert space, while on the other side I have a K bulk which is acting on the bulk Hilbert space. Yes. So I do know that these two spaces are isomorphic, but but that isomorphy is related using some unitary map, some U.
Yeah.
So is there some implicit U hidden in this expression?
Okay. So what I should say is that firstly, this statement is only a semi-classical statement. So you're correct that there's an isomorphism between the quantum gravity Hilbert space in the bulk and the conformal field theory Hilbert space on the boundary. In this case, we're only considering semi-classical states. So this is sort of what's typically called the chord subspace, which is a smaller subspace of the bulk Hilbert space. And you should think of this equation as acting only on that chord subspace. Once you do that, then this equation makes sense as it is.
I see. Okay.
Yep. Yeah, thanks for that. Was there any other questions? Okay. Good. So very nice. So once we have this operator equation, this is a pretty powerful equation because now we can stick this into any state. So we can compute the expectation value of this in any state, which is still, we're still restricting to the set of semi-classical states, but still it's a wide class of states that we can consider. And so now you see that the relative entropy had two kinds of terms. There was this trace rho log rho and trace rho log sigma. And log sigma and log rho are basically the modular Hamiltonians in the states rho and sigma. So if we have an equation for log rho and log sigma, we can compute its expectation value in the state rho and find the relative entropy. When you do this, you end up with the JLMS formula. This is how the original JLMS formula was found. Okay. But this isn't the complete story. We've understood over the years that there are corrections to this story. So firstly, the FLM formula is not really correct as it is to all orders in G Newton. Way back in the day, Engelhardt and Wall had proposed that the correct generalization of the FLM formula is the quantum extremal surface formula. In the quantum extremal surface formula, one has the same sort of behavior. It has this A over 4G plus S bulk, but one extremizes collectively over the sum of these terms instead of just extremizing over the classical part. And this was understood to be consistent with the FLM formula at leading order, but there were corrections at higher orders in G. This was the story back in the day, but more recently, people have understood that, in fact, the quantum extremal surface formula can be important even at leading order. So, for example, in the recent years, there have been these calculations of the page curve. And the page curve, as computed by these authors, and there's been a lot of work on it ever since, required the use of this quantum extremal surface formula. It was a situation where the quantum extremal surface formula gave a different answer from the FLM formula, even at leading order. And this was important for getting the page curve. So clearly, the FLM formula is not sacrosanct. It does get modified. And so there's no reason for JLMS to be also sacrosanct. It also should get modified since it required the FLM formula. And so an appropriate generalization of this, which to my mind was first proposed in this paper by Dong and Lukowitz, was to generalize the JLMS formula to include the effects of quantum extremality. This is what I'll refer to as the Q JLMS formula. So you can think of it as a quantum generalization of the JLMS formula. what does this say? So it just says that when we compute the relative entropy on the boundary, again, on say some region A, we have two contributions. As before, we have the expectation value of the modular Hamiltonian of state sigma, which is given by this equation in the state rho. And there's a term which is the expectation value of the modular Hamiltonian of the state rho in the state rho. These were the two terms that were part of the relative entropy. So the new modification is just that you include the fact that quantum extremality requires you to consider the sum of these two terms and then extremize it, as opposed to just considering the extremal surface for the classical part and then computing the quantum correction. So once you do that, there's two surfaces. There are two different surfaces that can show up. You can, when you extremize just this part, this is the usual entropy calculation. So when you just compute, when you extremize area over 4G plus log rho in the state rho, you end up with the quantum extremal surface. So this is the familiar thing from the quantum extremal surface formula. But there's something a little more unfamiliar, which is suppose for the other term, which was trace of rho log sigma. You now take log sigma, which is represented by this thing, compute the expectation value of in the state rho, and then extremize it, extremize this quantity. This gives you a different surface, which I've labeled gamma sigma, which in general can be different from gamma rho. At leading order, typically when the JLMS formula was computed, these two surfaces were identical. And so the contributions when computing the expectation value in rho would just cancel out. And then you would be left with just the relative entropy computed in the bulk. This is how the JLMS formula came about. But now these two surfaces can in general be different. And so you should account for the difference between these two surfaces, which comes from quantum extremality. But that's a straightforward generalization. So this was something that was already proposed almost 5 years back. And this is what I'll refer to as QJLMS. This is the formula that was expected to be true from the path integral once you include these effects of quantum extremality. Okay. All right. So
can I ask something here?
Yeah, sure.
So is there a way to, so when we talk about this corrections, the bulk part, are we including gravitons or not?
Yeah, that's a good question. So there's always been this subtlety about this. So whenever, when Engelhardt and Wall made this proposal for quantum extremality, their proposal was to all orders in G. So in principle, that would also include graviton corrections and interactions of the graviton and so on. But this has never been made crystal clear. So, I mean, in principle, because it's a gauge theory, the graviton is just another kind of gauge theory. What one has to do typically is include these edge mode contributions and do it in a gauge invariant fashion. This is something that has not been made explicit, but people generally expect that once you do that procedure, including these edge mode contributions and so on, it should be a well-defined entropy and it should be consistent with this quantum extremality. But I don't want to make claims about that because I haven't seen a very concrete calculation of this. But in principle, it's supposed to include that.
Okay, so in that case, the area will be basically an area operator, right? I mean, this
that's
is
right.
what
that's
they
right.
write, what they claim.
That's
so,
right.
So is it so? Okay, maybe I can ask it more concretely later. But a short thing to ask would be that. Suppose if you include this gravitons as a semi, is there a way to actually include gravitons perturbatively by putting in some? So there, of course, is zero modes or everything on the surface that can cause fluctuations of the surface. But but is there a way to? Is there some way to at least to do it at say leading order that you could think about?
Yeah. So at leading order, it's just a free field in the bulk, except that you have to be careful about gauge constraints. Some calculations to this extent have been done. There's a paper by Cassini who did this. I mean, you could consider the analogous problem for E&M. Like it's a very similar calculation where you just you have a U1 gauge field in the bulk and you want to compute the entropy that comes from that. That calculation has been done in a great amount of detail by Donnelly and Wall. And so you might expect that at least at leading order is just a free field, and a similar calculation should work for gravitons. And some, at least partial calculations of this have been done by Cassini, but there isn't a fully general calculation of this. And that's also at leading order. I mean, at higher orders, you have to include effects of interactions and so on, and then it's even more complicated. But it seems more like a technical problem than a conceptual problem as such. I mean, it's just that we haven't understood these corrections explicitly, but in principle, they should be similar to what you get for a U1 gauge field.
Okay, maybe I can ask more later. Thanks.
Okay. Yeah, thanks. All right. Yeah, but it's a very important point that you raised, which is we think of this this area as an operator which is acting on the Hilbert space in the bulk, which includes the gravitational part. So there's a classical piece, but then there's also graviton fluctuations and so on. And you should think of each of these as operators. Okay. Now, good. So there's a more direct way of seeing what I just said, which is there's a replica trick calculation for the relative entropy. So the replica trick is a very useful way to compute things. And for example, for the entanglement entropy, this is a familiar thing. There's a very similar thing one can do for relative entropy. Remember that there were two terms. There was this trace rho log rho term, which is the same as what one does for the entanglement entropy. So one just computes log of trace rho to the n. This rho to the n for integer n can be computed by replica trick. And similarly, for the trace rho log sigma term, one considers trace of rho sigma to the n-1. And again, computes this for integer values of n. Once you do that, you have to perform some analytic continuation, take the limit of n goes to 1. You have to define some procedure for this and so on. But once you do all of that, you get the relative entropy. This is just by definition. So in ADS-CFT, you could try to compute these two things. And the simplest way to do this analytic continuation was something that was proposed by Lukowitz and Maldacena, which was to assume that there's a bulk saddle that computes this answer, and it has replica symmetry. So in each of these calculations, you have n copies of the system, and you assume a Zn replica symmetry. So the boundary calculation has a Zn replica symmetry, and you assume that the bulk also respects this Zn replica symmetry. Once you do that, then it's not too hard to see that you get the quantum JLMS formula. Essentially, these two terms end up giving you the two terms that I told you about here. So the key idea is that the Euclidean path integral with the assumption of replica symmetry, so assuming this Lukowitz-Maldacena prescription for analytic continuation, gives you the QGLMS formula. So there's good reason to expect the QGLMS formula to be true. However, in the last few years, there's been a better understanding of the gravitational path integral and contributions to the gravitational path integral. And in particular, replica symmetry breaking saddles or just even non-saddles have played an important role. So since we have a more controlled understanding of the path integral in simple examples like Jakiv-Teitelbaum gravity and so on, people have been able to use this to exploit this better understanding of replica symmetry breaking contributions. And this has led to some interesting effects. For example, people have used this to compute the entanglement entropy and corrections to the quantum extremal surface formula, near phase transitions. That was done in these papers. In a paper with my collaborators, Chris Akers, Tom Faulkner, and Simon Lin, we did the same for reflected entropy. And again, there are interesting features that show up near the phase transition that very crucially rely on these replica symmetry breaking saddles. And similarly for entanglement negativity and so on. So there have been a lot of works which have used these replica symmetry breaking features and seen new interesting effects. So one reason to expect that there are corrections to this QJLMS formula is that replica symmetry breaking contributions can play an important role. So it's useful to do this replica trick, but now include all of these other contributions in as controlled a way as possible and see what they lead to. So that's sort of the Euclidean philosophy on how we're trying to understand this problem. Okay. All right. So there's a more Lorentzian way to understand the way we're thinking about this problem, which is the perspective of quantum error correction. So quantum error correction, there's been over the last decade or so, people have tried to understand holography in terms of quantum error correction. And the idea is pretty simple. It just says that, as we discussed before, there's the sense in which the region in the bulk that's dual to this boundary region is the entanglement wedge. And the sharp way of phrasing this is the statement of subregion duality. Subregion duality basically says that if you want to represent an operator in the entanglement wedge, you can do so on the region capital A without having any support on A bar. So there exists a reconstruction of this operator, which acting on the bulk Hilbert space. There's a reconstruction of this operator on the boundary Hilbert space, which does the same action on the boundary Hilbert space as the operator O little a does on the bulk Hilbert space. So there's a mapping of these operators from the bulk to the boundary, which respects this subregion duality. Operators within the entanglement wedge can be represented purely on this subregion. That's the statement of subregion duality. And in a variety of papers, it was shown that this is actually in one-to-one correspondence with the existence of a Ryu-Takenagi formula with FLM corrections. So there's a very nice paper by Daniel Harlow, especially, which showed this. And once, as we discussed before, once you have the FLM formula, then you get the JLMS formula for free, and these are in one-to-one correspondence. And so there's a tight connection using this quantum error correction idea between all of these three things. And more so, what it says is, in trying to derive any of these properties, one just used very general features of quantum error correction. And so each of these things, the Ryu-Takenagi formula and the JLMS formula, are sort of universal features of quantum error correction. Any quantum error correcting code which has this subregion duality property, has an analog of the JLMS formula. Okay. Now, an important thing is that whenever all of this analysis was done, it was in the regime of exact quantum error correction. So people always consider the situation where there's an exact isometry between the entanglement wedge and the boundary subregion. But over the last few years, people have understood that it's not super important that there's a structure of an exact quantum error correcting code in holography, especially because there can be perturbative and non-perturbative corrections to, for example, the FLM or JLMS formula, which we discussed. For example, the feature of quantum extremality is something that falls in this category. And the only way to understand that is there's still some sort of quantum error correcting code-like structure, but it's only approximate. There are perturbative and non-perturbative corrections that break this code, even if it's in a small amount, even if it's by a small amount. The interesting thing is that this can then lead to new features because it has a much richer structure. Approximate codes have much more novel features that you wouldn't find from just exact error correcting codes. And an example of this is in a paper by Hayden and Pennington. They showed that when you have a bulk code subspace, which is large, then sometimes you can be in a situation where you require a state-dependent reconstruction, which essentially says that this operator that we wanted to reconstruct on the boundary, you can reconstruct this operator such that it acts correctly when acting on some set of states. But if you then choose a different set of states, the reconstruction of the operator changes. This is what people mean by state-dependent reconstruction. It essentially says that the main mechanism by which this happens is when you try to reconstruct this bulk operator on the boundary, there's a small error. And when you try to make this operator consistent across a large number of states, the errors can accumulate and become important. And if you consider a large enough subspace, then there's just no reconstruction that's state independent. Was there a question? Okay. So that's sort of one feature that approximate error correction buys you. This, by the way, is never possible in an exact error correcting code. An exact error correcting code just has state independent reconstruction. So this is one interesting feature that we learned about ADS-CFT from approximate error correcting codes. And there's more things along this line where you can take this to greater extremes. And in this paper by Akers and Pennington, they showed that sometimes you can't even define the entanglement wedge properly. You can have what are called these incompressible states, which don't have a well-defined entanglement wedge and hence don't have a well-defined quantum extremal surface formula. The quantum extremal surface formula fails. And it was understood that one has to restrict the class of states to exclude these incompressible states. And under such an assumption, one can then prove the feature of quantum minimality directly from the quantum error correcting code structure. So one can again consider an arbitrary quantum error correcting code and show that the feature of quantum minimality shows up as a universal feature of such codes. So each of these things really required us to go away from the regime of exact error correcting codes and move to approximate error correcting codes. And so this is in going with the fact that subregion duality or bulk reconstruction is very closely tied to the JLMS formula. So in exact error correcting codes, one has the exact JLMS formula, which says that the bulk relative entropy is the same as the boundary relative entropy. This statement, I mean, it's been known in the quantum information literature for a long time that this implies that there's a reconstruction map, the so-called PETS map, which works exactly. So you can use this PETS map to reconstruct bulk operators on the boundary. When you have approximate error correcting codes, then this statement is only approximately true. But even if it's approximately true, it was shown in this paper that there's actually a slight variation of the PETS map called the twirled PETS map, which still works very well. So if you have the JLMS formula true to some epsilon, some small correction, then you can still prove bulk reconstruction using this idea.
Pratik, I have some comment on your previous on this slide. So there are two separate issues, right? One issue is about the state dependence, which is related to approximate error correction, because without that, you cannot even talk about state dependence.
Yes, yes.
However, there is another thing about this fact about exact versus approximate reconstruction, right? And these two need not be this overlap. I mean, you can have state independent approximate error correction, which I think, so in the context that you were talking about, right? Obviously, non-perturbative or some gravity corrections will make the reconstruction only approximate, but not necessarily state dependent. But in case you have horizon or some, then the issue changes, because then you can have multiple extremal surfaces. And yeah, so you agree these two are separate concepts?
Yeah. I think I completely agree with what you're saying. What I wanted to say was that this feature of state dependence couldn't have arisen without this approximate. I mean, as you said, like you could have approximate codes which don't have this state dependence. For example, if your bulk code subspace is small, then you won't ever have this issue. But having an approximate error correcting code allows you to have these large code subspaces where errors can accumulate, and you would need this feature of state dependence. So I just mean that in the absence of an approximate error correcting code, you wouldn't have this feature of state dependence. You could, of course, have the approximate independently of that. Yeah.
Okay.
Yeah. Thanks for that. Good. So getting back to the bulk reconstruction, as I said, the exact JLMS formula implies an exact reconstruction. The approximate JLMS formula implies an approximate reconstruction, as was shown in this paper. And so it's important to understand whether the JLMS formula is actually has large corrections, or can it fail at some point, and things like that, just because it puts a lower bound on the fidelity of reconstruction. So having something like a JLMS formula guarantees bulk reconstruction, even though the failure of the JLMS formula doesn't necessarily preclude reconstruction. But it's always nice to have something like the JLMS formula, just to understand that, just to have the guarantee that we can reconstruct something in the bulk. All right. Okay, so there were these two perspectives, and the goal of this talk would be to understand corrections to the QJLMS formula. So importantly, I told you that the JLMS formula itself was modified to the QJLMS formula to include contributions from quantum extremality. And this talk will be about corrections to the QJLMS formula itself. And the way we would like to understand these corrections is, again, in two ways. There was the Euclidean perspective, which was to say that we can include replica symmetry breaking effects in the gravitational path integral, which then leads to some corrections to the QJLMS formula, which followed from replica symmetry. And the Lorentzian perspective of this would be to understand just the general mechanism of how such corrections can happen from the viewpoint of approximate quantum error correction, because exact error correction led to JLMS, and once we moved away from that, then there could in general be corrections to the JLMS formula. All right, so this is sort of the goal of the talk. So now let me give you an outline of the main the results that I'll discuss. All the calculations that I'll talk about will be in this model, the so-called PSSY model of black hole evaporation. So first I'll review what this model is and how we do the calculations that we need to do. And then in this model, I'll show you more explicitly how the QJLMS formula follows from the replica trick when you assume replica symmetry. And then, having done that, I'll show you how we find corrections by including replica symmetry breaking effects. So there'll be broadly 4 kinds of corrections that we find. There are these subleading saddles in general. So whenever you have 2 competing extremal surfaces, you'll have two kinds of replica saddles, which always at least lead to non-perturbatively small corrections. And the second kind of correction is where you have fluctuations of the area. So related to what Ayan was asking about, graviton fluctuations, or in general, the area of any given surface in the bulk has fluctuations of order square root g. And those fluctuations can become important near a phase transition. And these lead to corrections to the relative entropy of order 1 over square root of g, as I'll show you. Then we can have these corrections that come from incompressibility, which was a feature I told you about, that comes from approximate error correcting codes, where you can have even larger order 1 over g effects that correct the JLMS formula. And finally, the most novel kind of feature that we find is what I'll call rank deficiency. So this will become more clear when I discuss the particular example, but there's a certain kind of discontinuous behavior of the relative entropy, which can allow for arbitrarily large corrections to the JLMS formula. And this will sort of be the most important kind of correction that we find. And finally, I'll just summarize and talk about the implications of these corrections. But is that clear?
Pratik, just one thing. So it might be a good thing if we can finish in 20 minutes so that we have time for some discussions too.
Sure. Yeah.
So
yeah, I'll mostly
maybe
just
if you could just because PSSY model we know a little, so maybe you could just be focused on the kind of things that that's new results.
Okay, sure. Yeah. I just wanted to make sure that we're all on the same page. If everyone's happy with that, then I'll just briefly review these parts and then talk about the main results. Good. So hopefully everyone's familiar with this model. The model is that of Jakiv-Teitelbaum gravity coupled to end of the world branes. The action is pretty simple. It has this topological term, which leads to, which basically suppresses higher genus saddles by powers of e to the s naught, where s naught is this parameter. Then there's the usual JT action, which leads to dynamics of the dilaton in 2 dimensions. And it's coupled to this end of the world brane, which has some mass mu, which fixes the location of the brane. And the important thing that I want to talk about in this model is how to think about the code subspace. The code subspace of this model is defined by introducing flavor indices on the brane. So the end of the world brane carries some flavor indices. So there's some label attached to each of these branes. And they're of 2 kinds. There's what I'll call frozen indices. So there's K of these frozen indices. And there's some number D code, which is the dimension of the code subspace, number of fluctuating indices. So what exactly do I mean by that? So the states that we'll consider in this code subspace are of the following form. So a state psi labeled by some index A is of the following form, where we have all the frozen indices, which are these I labels, entangled with some radiation Hilbert space that's external to the system. So there's some auxiliary radiation system where the label I is entangled with the frozen flavor index on the brane. And there's some fluctuating label, which we can think of as the code subspace. And we can pick arbitrary states A, that label, that it forms a basis for a code subspace. So the bulk states you should think of as choosing different states on this A label, and then mapping to the boundary. And these form the code subspace on the boundary. These states psi IA are what are just prepared by the gravitational path integral. So in the gravitational path integral, one basically provides asymptotic boundary conditions that are dictated by the state. The asymptotic boundary conditions are the usual ones. They essentially impose some either canonical or microcanonical boundary conditions on the asymptotic boundary. And they have some labels which dictate what the flavor index on the brain is. So that's the model. And just for usefulness, the states essentially look like this, where you have a two-dimensional black hole. This red boundary is essentially it corresponds to an analytic continuation of this Euclidean boundary. And the labels here are of these two kinds: the A labels, which you can think of as bulk excitations or code subspace excitations, and there's this entanglement of the frozen indices with the radiation. This is just a useful tensor network representation of this same state. So if this helps you, good. If not, don't bother about it. All right. So hopefully this is familiar to you, where we can just take the states defined in this way and compute the density matrix. So the density matrix on the radiation has a diagrammatic picture which looks like this. We have some labels I and J for the density matrix, and further there are these fluctuating index lines which carry some indices, and this notation just says that we sum over the index lines here with the appropriate weighting factor given by rho. So the bulk density matrix gives you some weighting factor for the two fluctuating indices. All right, good. So now we can just do the replica trick that we discussed before. The relative entropy for this between these two states, rho and sigma on the radiation, can be computed using these two terms, which are rho times sigma to the n-1 and rho to the n, which correspond to boundary conditions of this form. So in each of these, so for example, for n equals 4, we have these 4 boundaries. We have these 4 asymptotic boundaries, which are glued together cyclically to implement the trace, and they're labeled by the appropriate bulk state, either rho or sigma. So this is some straightforward calculation where you can just find out what the asymptotic boundary conditions for this are. And then what gravity tells you to do is take these asymptotic boundary conditions and fill them up with all possible geometries that contribute to them, and then integrate over all these geometries to find what the contribution is. Okay. So the first thing that's straightforward to see is how the quantum JLMS formula arises. So if we just look at the replica symmetric contributions, there are two such contributions. One is the fully connected geometry, and one is the fully disconnected geometry. This should be familiar from the page curve type calculation. This is exactly the same as that. So when we compute trace rho to the n, appropriately normalized, in the Lukowitz-Maldacena approximation, we just maximize over these two geometries. The contribution from this geometry is there's a factor of Zn, which is the n boundary partition function, since we have a connected geometry that ends on n asymptotic boundaries, normalized with a factor of Z1 to the n, which comes from this trace rho to the n, times the contribution from the bulk state. The bulk state, because of the index contraction here, which follows cyclically, leads to a factor of trace rho bulk to the n. So that's this contribution. On the other hand, when we look at the fully disconnected contribution, it just has 4 separate asymptotic boundaries. So that just cancels out with the normalization. And then we have some loop counting function. So the number of loops gives you a factor of k. So there's one loop which gives you this factor of k with respect to the normalization. And further, now each of the rows are only connected with themselves. And so you end up with n pairs of trace row. Okay, so that's the contribution from each of these. When you now each of these is some analytic function in n. You can analytically continue to n goes to 1. When you do that, as expected, you just end up with the QJLMS formula. Okay. Any questions at this point? All right. Good. So now we come to the non-trivial part, which is including the non-replica symmetric contributions. These contributions in general can be classified by looking at how the different boundaries are connected with each other. So the calculation of trace row to the n is a sum over all the different topologies and all the different ways in which they're connected, which can be classified by looking at the permutation group. The permutation group essentially classifies how all the different ways in which they can be connected. And when you sum over these topologies, there's two kinds of factors that you can get. You get index loops of the frozen indices, which leads to powers of k. And the number of such factors depends on the number of loops that you have in the diagram. And then there's a product over each of the cycles. So for each connected geometry that you get, which has ni number of asymptotic boundaries, you get the ni boundary partition function, Zni, times the contribution from the bulk density matrix, which is trace of rho to the ni. So this is just the general contribution that you get for any such topology. And then you sum over all of these topologies. One important thing to note is that these n boundary partition functions can be computed with different boundary conditions on the asymptotic boundary. And typically what we'll consider is either the canonical boundary condition or the microcanonical or fixed energy boundary condition, in which case these calculations are tractable. So just as an example to tell you how these calculations go, this is an example diagram which will contribute. You get a contribution of Z3. So this is a 3-boundary connected geometry. So you get a contribution of Z3 from this region times trace rho cubed because of these 3 boundaries. Each index factor of the frozen indices corresponds to a factor of k. So each of these is a k. And then again, this single connected geometry gives you a factor of Z1 times trace rho. And there's a 1-to-1 correspondence between the way in which this geometry is connected and a permutation group element that you can write down on 4 entities, which basically tells you that the way in which these boundaries are connected is is represented on some permutation of these n elements. There's a similar calculation you can do for the other term. So the replica trick had these 2 terms, trace rho to the n and trace rho sigma to the n-1. There's a similar calculation you can do, and you can completely classify what the contribution from each of these geometries is. So now we have all the ingredients, and now we can just apply it to different situations of rho and sigma and see what kind of corrections we can find. Okay, so that's how we'll get our results. Okay. So the easiest thing to see is the small corrections which come from subleading saddles. Generically, they're just non-perturbatively suppressed. And the easiest example with which we can see this is if we consider rho and sigma to be just different pure states in the microcanonical ensemble. So for pure states, which are different, the relative entropy computed in the bulk is infinite. This just says that pure states are very easy to distinguish. You just need to do a measurement in the correct basis, which can distinguish between these 2 states. And what the JLMS formula then says is that when the number of frozen indices is less than the black hole entropy, or before the page time, which or in other words, when the radiation does not have an island, it's impossible for the radiation to distinguish between these two states. And so the relative entropy computed on the boundary should be 0. On the other hand, when you're after the page time, so when the number of frozen indices is larger than the black hole entropy, the radiation includes the island. And so the bulk state is part of the entanglement wedge of the radiation. And since the bulk relative entropy was infinite, the boundary relative entropy should also be infinite. So this is the prediction from the quantum JLMS formula. When you actually include these subleading saddle corrections, what you find is it's true that you have infinite relative entropy beyond the page time, but there is actually a non-perturbatively small tail of the relative entropy, which you find even before the page time. So there's a non-perturbative correction to this quantum JLMS formula, which essentially arises from the existence of these subleading saddles, which are some wormhole-like geometries. This calculation is pretty general. I mean, because you're working in the microcanonical ensemble, you can argue actually that even in higher dimensions or in more general settings where you have two extremal surfaces, you can replace all of this technology by using fixed area states, which were described in these papers. And the calculation is pretty identical. The same kinds of saddles affect the answer, and you still find these non-perturbatively small corrections. So that's the 0th order thing. That's the easiest thing to find. Now there are more interesting and larger corrections that you can find. And these come from area fluctuations. So the area of the extremal surface has some width. I mean, when you consider the canonical ensemble, the area has some width of order square root g. So it has some graviton fluctuations can give it some width. And what this says is since there's a distribution, there's a thermal distribution of the value of the black hole area, different parts of the wave function will actually undergo the phase transition or the page transition at different times.
Can you explain one thing, Pratik? What do you mean by the graviton in this JT model?
Yeah. So here, what we really mean is that, I mean, the only dynamical degree of freedom here is the dilaton.
Parametrization. The time parametrization.
Oh yeah, sorry. So that's true, but I just want to take a bulk perspective where we just think about it in terms of the dilaton. And the analog of the area in this model is the dilaton. So when we say the RT formula or anything like that, what we mean is instead of the extremal area, what we're computing is the extremal value of the dilaton. And in this model, there are fluctuations to the value of the dilaton of the order of square root g. In 2 dimensions, just whenever I say area, just replace it with dilaton.
So how you're estimating the area fluctuations? You're simply evaluating the value of the dilaton at the extremal surface, and then you are saying that how that due to fluctuations, how that value at that point, what is the typical fluctuation of the value of the dilaton? Yeah.
So you can compute, for example, the standard deviation of the value of the dilaton at the horizon. In JT, there's a direct relationship between the energy on the boundary and the value of the dilaton. Like there's a 1-to-1 correspondence between these two things. So you could equivalently just look at the spectrum of energies on the boundary. And for that, there's a much easier there's a much simpler argument to say that the width of that is of order square root g. So
this is the typical what we call the 1/n corrections. That
exactly. I mean, yeah. That's exactly what it is. I mean, this is just the general statement that in the thermodynamic limit, variances are 1 over n suppressed. It's just that. I mean, you can estimate the variance just from that.
Okay. All right, but okay. Let me ask maybe. So is it so the point where you are actually evaluating it itself can fluctuate, right? I mean, it's not only the the value of the flux. How do you? I mean, okay, maybe it's not be of the same order, but is there a good way to argue it will be of the same order?
Here it was more of an indirect argument, but I mean, in general, there's a very general argument for this, which is that the way you should think about a bulk geometry is it's like a coherent state of the metric, and in a coherent state, the width is like order square root h bar. If you look at either of the variables like x or p, they have a width of order square root h bar, and it's just the same general mechanism that works here. I mean, you just look at the Poisson brackets and they have the same structure. And so whatever you say there can be imported here. So this typical smooth states that you prepare have this variance.
Yeah, if you just make an order of magnitude statement, I don't think that anybody will disagree with it. Okay.
Yeah, no, I think this is just an order of magnitude. I mean, all I want is an order of magnitude estimate. You could try to do this calculation more precisely. I mean, in principle, what you can do is you integrate over all geometries, and as you said, like the location of the surface itself can fluctuate. So you just go to each geometry, which may be off shell, and evaluate what the area or evaluate the value of the dilaton at whatever the extremal point is, and then look at and integrate this over the entire space of geometries. This is a pretty hard calculation, and I haven't seen it being done. But so for most purposes, we'll just be looking at the order of magnitude.
Okay.
There's another calculation that was done in a paper by Don Marolf where
why I'm asking this question, let me be more precise, because so one thing about this JLMS formula is not only that that the bulk and relative entropy are same, but also there's a clear separation between two things. One, there's special contribution that comes from the surface, extremal surface, and there is something that comes from the bulk. So there are two precise pieces. You know where they are coming from. So I was thinking if you could somehow take into account this one over G corrections precisely as some change to the area operator or something that you can something that you can compute there. And also the other thing that I don't understand in this argument, it's a very subtle thing, and I think this is also important. So if you are looking at fluctuations of this kind, graviton, you can either think of it, you do not know where to actually include this. One place to include it would be to in this entanglement wedge itself, and the other would be the entanglement wedge of the Hawking radiation, right? So what I don't understand is how do you separate these two in a useful, because if you look into this original formula for this bulk versus thing, so the quantum extremal surface of this thing is exactly the quantum extremal surface of the complement, right? So I don't understand how that goes through once you include this area fluctuation. So that may be something that is a finer question based on like how to think about the area fluctuations more precisely. But if you're just making an order of magnitude statement, then all these subtleties are not.
Let's see. So I'd like to say maybe it's a stronger thing. So, okay. Firstly, the area fluctuation. So that statement that you said, which was that the quantum extremal surface is the same for both sides, is true when you have a well-defined entanglement wedge. So when you have that, the area fluctuations don't really affect anything. I mean, that's like being in the previous situation where you're not near a phase transition and all you care about is which one is the dominant extremal surface. The area fluctuations don't really affect the answer for the entropy too much. So in that case, you can just define. In principle, there might be subtleties to this, but I mean, in principle, you could define a factorization in the bulk, which factorizes the Hilbert space across this extremal surface, including all the graviton fluctuations. In that case, the graviton, I mean, there'll be some edge mode contribution, which will again localize to the extremal surface, and there'll be some quantum fluctuations which are more like the bulk term, as you were saying, like there's some separation between the bulk term and this boundary term. But you could imagine doing that calculation, and I don't see any obvious problem with that.
Yeah, but the edge mode that are localized only on the surface, where do you include? Do you include them in the contribution to this to this side or that side?
Well, they're shared. I mean, they're on the surface, right?
Yeah. So this is this I understand. So they will. So in principle, will include it on both sides equally.
Yeah.
Like you include the root Akanagi area formula equal.
Exactly. I mean, it's exactly analogous to that. Like, I mean, people have said this for a while, where the idea is that somewhere in the UV, like the Ryutakanagi formula itself is some edge mode type calculation. And all you're doing is like, I mean, there's some gauge constraint, which is relating the fields on both sides. And the Ryutakanagi is the entropy that's coming from the fact that these are correlated. And you would say the same about like adding graviton fields perturbatively as well. Like there's some gauge constraint which would relate them on either side, and there's some edge mode contribution localized at that surface that contributes to both.
Okay, but this separation between these two can only make sense perturbatively, right? I mean, only in the 1/n expansion. So that you say that, and this perturbatively you can make some sense of this separation of on this side and that side, make it precise.
Yeah, I agree with that. I mean, certainly not clear what happens non-perturbatively. I mean, our semi-classical understanding itself is like only order by order in 1/n. I mean, if you're talking about like very non-perturbatively suppressed things. But yeah, I could imagine that. I mean, at least in order by order in 1/n, that should make sense. At least I don't see any obstruction immediately.
Thanks.
But more so, just going back to your previous question about like where the square root G comes from, what I wanted to mention was, there's this calculation again by Don Merolf, where what you do is you just use the path integral where you project onto specific values of the area. So just like what I was discussing about fixed area states, where you have some boundary conditions that prepares your state, you project onto definite values of the area, and you find the amplitude of getting that state. So what you're doing then is finding the distribution of areas by looking at the probability of finding each value of the area. When you do this, what you find is that there's basically, I mean, it peaks at the value of the semi-classical geometry, and there's some Gaussian spread in areas around that value. And you can, just from the semi-classical calculation, you can find what the variance of that Gaussian is. So at leading order, I mean, there are obviously corrections to this from all the things that you said, like graviton loops and so on. But at leading order, you can estimate this just from the semi-classical path integral, just by a classical analysis. And that gives you some precise coefficient for what the variance in the area should be at leading order. And that's what I mean here by area fluctuations.
Okay.
Okay, good. So the key point is that this is some very general mechanism. I mean, this happens. This has been argued to affect, for example, the entanglement entropy calculation very universally. When you look near entanglement phase transitions, these area fluctuations. These area fluctuations become important, and you can see the effect of these square root G corrections. In this model, we can see the same thing. For example, if we take rho to be some pure state and sigma is, let's say, a maximally mixed state, just for convenience. I won't go through the details, but I'll just show you the plot. When you plot the relative entropy as a function of k, which basically tells you where in the phase transition you are, very early on, you just have non-perturbatively small relative entropy, like in the previous example. But then when you're close to the transition point, note that for a large enough code subspace, the location where the phase transition for rho happens and the place where it happens for sigma are separated. These are at two different locations because the quantum extremal surface dominates at different locations. One of them is given by the black hole entropy, and the other one is given by black hole entropy plus the entropy of the mixed state itself. So there's two different locations where the transition happens for the two different terms, trace rho log rho and rho log sigma. And more so, near each of these transitions, there are these corrections to the entropy, which scale like order 1 over square root g just from these area fluctuations. So what you end up finding is there's two locations, there are two transitions, and there are two locations where there are these corrections. So you have an increase, which has some corrections because of the first phase transition. And then there's a saturation to the value predicted by the JLMS formula. And that happens again with these order 1 over square root g corrections. So there are large corrections near these phase transitions, which follow from this general mechanism. All right. Good. Now let's look at even larger corrections, which essentially come from these incompressible states that I talked about. Now, incompressible states, I mean, a very simple, intuitive way to understand them is that these are states which cannot be approximated just by truncating to an e to the s dimensional Hilbert space. So an example of this is, let's say you have a density matrix, which is a mixture between a pure state and a maximally mixed state. So let's say we have some order 1 probability, like you can take it to be half or something. It's easy to compute the entropy of this, and at leading order, it's basically given by 1 minus p times log of the dimension. So, if it were a compressible state, then you should be able to truncate it to an e to the s dimensional Hilbert space. But now notice that e to the 1 minus p log d is actually much smaller than the dimension of the Hilbert space. But if you were to truncate to such a small Hilbert space, you would lose a large part of the wave function, which has support on the entire Hilbert space, which is this mixed state. So this is just an example, and there are many other such examples. Generic states actually have this feature where you can't actually truncate it to a small e to the s dimensional Hilbert space. Although in holography, very often we consider states that are like that. So each of these states individually, the pure state and the maximally mixed state, are actually compressible, and they have nice formulas associated to them. But the insight in the paper by Akers and Pennington was that you could consider more general such states, and then they're incompressible, and the quantum extremal surface formula fails for such states. There's no well-defined entanglement wedge. And there's the quantum extremal surface formula itself fails. So clearly, since the quantum extremal surface formula fails, the quantum JLMS formula, which essentially followed from the quantum extremal surface formula, should also fail. And that's what we find. We find order 1 over g corrections when the transition for rho happens, because rho is the incompressible state. On the other hand, sigma was chosen to be maximally mixed, and maximally mixed states are compressible states. So we don't find large corrections when the sigma transition happens. But still, the important point was that when you have incompressible states, there are locations where there are order 1 over g corrections to the quantum JLMS formula. Okay, good. Now let me finally come to the last kind of violation of the JLMS formula, which arises from what I call rank deficiency. This is, I mean, all the other mechanisms that I talked to you about were things that were sort of expected or had been seen in other settings. The rank deficiency one is the most novel kind of effect that we found. And a simple way to understand it is to think about what happens in the canonical ensemble. So in the canonical ensemble, the black hole it has a thermal spectrum. And a thermal spectrum has an infinite number of eigenvalues. However, when you're trying to entangle it with a finite dimensional Hilbert space, the density matrix only can have finite rank. I mean, there's a Schmidt decomposition that you can write down between the radiation system and the black hole system. And since the dimension of the radiation Hilbert space is finite, it's k, the density matrix of the black hole Hilbert space can't have a higher rank than that. So what ends up happening in the spectrum is the system takes the infinite thermal spectrum, truncates it at the largest k eigenvalues, and then appropriately normalizes it. So the spectrum looks like this, where it's like the thermal spectrum, but it has a cutoff at some location. So that this is just a finite number of eigenvalues. Now, the important feature is, all of this was true even in the entanglement entropy and island calculations. But the important thing there was that the consideration, the entanglement wedge is determined by entropic considerations and not by rank. The rank, it was just a cute feature that there was this finite dimensional spectrum. But here it actually becomes very important. And the reason is that no matter what states we consider, the density matrices of the radiation have no zero eigenvalues. The cutoff thermal spectrum is strictly, it has all eigenvalues strictly above zero, because it's trying to accommodate for this infinite thermal spectrum. And so there's no zero eigenvalues. There's no
sorry,
kernel.
can you explain where the cutoff comes from?
Yeah, so this comes from a calculation. So in the PSSY paper, they do this resolvent calculation to extract the spectrum, which gives them this particular spectrum. But an intuitive way to understand it is just to see that since the radiation can accommodate for k eigenvalues, it just accommodates for the largest k eigenvalues. It just keeps the largest k eigenvalues of the thermal spectrum and then truncates everything else. That's where the cutoff is. So the cutoff is determined by the rank of the radiation Hilbert space.
Yes.
Does that make sense?
Yes. So that goes into this trace computation that you are doing for the saddles, for wormhole saddles.
Yeah. So I was just getting to that. I mean, so for this calculation, we don't even need to do the path integral calculation to see that there's a large violation. There's a very universal way to see the violation. And the way to see the violation is once you have this spectrum, the important feature is that the density matrices have no zeros. They have a strictly positive spectrum. So now what we can do is pick bulk states, which are, let's say, pure states, for example, and they're like, let's say, two different pure states. Two different pure states in the bulk will have infinite relative entropy. But since the boundary density matrix has no, and the only way in which relative entropies in a finite dimensional Hilbert space can be infinite are because of zero eigenvalues. The log sigma term, whenever you hit a zero, is infinite. So if rho has support in a region where sigma is zero, then you get an infinity in the relative entropy. But for that to happen,
so one question that can appear is that you are assuming there is some reconstruction, right? In this, but for the singular kind of states, but there may be no good reconstruction anyway.
There is reconstruction here because this is just the page curve calculation. So this spectrum is true for.
This I understand, but I'm saying that for the specific examples that we're talking about, like only one spin somewhere and another, like order 1 degree of freedom only, like what you call incompressible, like. So there may not be any good reconstruction in the first place, right? I mean, there is no proof that there will be a reconstruction.
No, there is actually. So I mean, this is no different from just, I mean, okay. So what we're considering is we're way past the page time, and there's a well-defined entanglement wedge. And we can do this for arbitrary states within this Hilbert space. Like we can just project the brain onto some particular state. And these were all part of the code subspace. So the code subspace was defined to include all of these semi-classical states, and these are just part of that subspace. They're not any more singular than any of the other states.
No, in this PSS, for example, I understand. But suppose you have real bulk matter, then there is no guarantee that
I see.
kind of singular states can be reconstructed.
I'll get to that. Let me just complete the model, and I'll get to how we find more general situations. Yeah. So in this model, firstly, I wanted to argue that here you have finite boundary relative entropy because there are no zero eigenvalues, but the bulk relative entropy is infinite. And so this is an arbitrarily large violation of the quantum JLMS formula in a regime where you wouldn't expect it. It's a regime where the entanglement wedge is very well defined. It's a compressible state and so on, and there's no problem with the state. But still, you find that there are large corrections to the JLMS formula. And then you can write down many variants in this simple example. Now, coming to the question of more general setups where this is true, the important feature that showed up in this example was that the entanglement wedge was determined by entropic considerations and not rank considerations. So anytime you can write down states, which we don't need to have something like a pure state or anything like that. We can write down well-defined QFT states, which can still have infinite relative entropy in a given region. And just from general arguments, we can restrict to a finite dimensional Hilbert space on the boundary just by imposing some cutoff or something to recreate the fact that there was a rank constraint which came from the fact that the radiation Hilbert space was finite dimensional, and that's all we really need. All we really need is that there's a rank constraint coming from a finite dimensional Hilbert space, and which makes the boundary relative entropy finite, while the bulk relative entropy can be arbitrarily large. That's all we need.
Okay, so just a nice question. I mean, why should this Hilbert space of radiation be finite dimensional anyway? In a reality, I mean, this is not something that we expect to be finite dimensional.
So for
in
example,
this specific cartoon, it is, of course. I mean,
yeah. So what you could do is, I mean, we sort of do this all the time, right? Like you have any system, you can always truncate it. So for example, if you collected the radiation in some box and you restrict it to some band of energies, that would be a finite dimensional Hilbert space. You don't need to consider all the infinite degrees of freedom in QFT. Like when we do this in a lab, like we just have some spin system which approximates that system. So I mean, I could just collect all the radiation into a spin system and it's finite dimensional.
So then you are having both infrared and ultraviolet cutoff, I guess, in this way of thinking. And then, but then still, I mean, these kind of considerations. I mean, when we are putting this cutoff, then that it's not quite clear what is the analogous thing in the bulk that we are doing when we are varying these cutoffs. And so I guess it's in reality, I don't see how this rank constraint might be really important.
Sorry,
at least for radiation.
Wait, sorry. Do you agree that? So let's take a more realistic model of radiation where it's not the PSS5 model. Let's say you just have some ADS where you suck out the radiation into some other system, and I just want that system to be finite dimensional.
But why should it be finite dimensional if the radiation? I mean, the radiation is like any quantum field theory Hilbert space, and it's not finite dimensional.
I mean, but
or you could make it if you make a lattice or something like that. You put then that's fine. But this is not a lattice. I mean, these kind of this is with gravity. We don't know how to make a lattice version of this. things. I mean,
Oh, no. Sorry.
conceptually.
But when we're saying like we extract the radiation and put it in some auxiliary Hilbert space, we don't need that to have gravity, right?
That's true,
We can,
but that typically does not have any finite dimension. It's infinite dimensional space. Yeah,
I don't
space.
see why you need that to be the case. Like, I mean, any realistic experiment that we do is always a finite dimensional thing, right? I mean, you work in the lab and extract the radiation, put it somewhere. You can,
Yeah,
I mean,
there are many things, but this is I think in this case, at least for the, I mean, whenever we take this like black hole or this kind of scenarios, where we're always taking a very large n limit, and typically we're always expecting an infinite dimensional space. But okay, there can be some ways to regularize it, like making it finite dimensional, and as you're saying that. But then I don't see how that comes into this specific. I mean, there is some order of limit issue that I'm worried about.
Sorry, so your issue is with the n goes to infinity limit, or like the usual, like even in a field theory, you have infinite dimensional Hilbert space as such.
Yes.
What I want to do is truncate that to like a finite dimensional by, for example, putting a restriction on the energy or something. There's a separate consideration which if n goes to infinity is it's like a different divergence. But at finite n, this is okay, right?
Well, but still, I mean, even if you put a cutoff in k, you still have to discretize this, right? I mean, you have to put it in some. Just by putting a finite cutoff itself doesn't make it finite dimensional. You still have infinite number of values of k between 0 and say lambda, and then you have to probably, what you mean is to put some kind of a lattice version of this, or make a lattice version of the whole thing, which is, I think, very clear how that should be done.
I think this is like sort of the working assumption under, like in most of black hole information discussions, right? Like we like the canonical model of this thing is like Page's bit model, where we consider like the black hole is just spitting out some qubits every once in a while, and that's like explicitly finite dimensional all the time. You can raise issue with that. I mean, but then you should be bothered by Page's calculation as well.
No, I'm not bothered by the Page's calculation, because that's sort of a well-regulated limit in the sense the order of limits is clear. Like we first you first think of a finite dimensional system, and then you are making it large. But here you have taking some order of limit where some of the degrees of freedom are large, some of the degrees of freedom are small, and this makes me uncomfortable. Because you see, I mean, this is what, I mean, here you are considering some radiation, and the radiation in principle will also include, in principle, the time reparameterization modes or whatever. In general case, it will also include gravitons and whatnot. So in this case, it's not clear, like how are you, in what order of limits you could take such that you could keep one of the systems finite dimensional and one other system still large n, and
I see. Okay. Maybe this makes you happier. Okay. So what was important here? Maybe your issue is that you're not so unhappy about one being finite dimensional. You're unhappy that the other one is then infinite dimensional. Is that
exactly
the issue?
Exactly?
Okay, good. So let me then say something else, which is we can do something where let's say I take k to be much larger than e to the s, which ensures that okay. Let me do this thing where I modify the black hole spectrum. So I impose like a IR and UV cutoff also on the black hole. So I don't have an infinite thermal spectrum. I have some finite thermal spectrum, let's say. Okay. And in that, so I truncate the black hole spectrum to some range of eigenvalues, which has some rank of the black hole. Let's say it's some k1, something like that. And I want to be in a regime where the k of the radiation is much smaller than k1, but much larger than e to the s black hole. This is all I need. So the fact that it was infinite was not super important. What was important was that it had more eigenvalues than the radiation system. this already ensures that there's no zeros, because what it then tries to do is accommodate all of the eigenvalues within its k-dimensional Hilbert space, and then there's no space left for any zeros. So it doesn't strictly have to be infinite. All that was important was that there were two parameters in the problem, the rank and the entropy, which are independent. Like you can tune those independently, keeping both finite if you like. And that leads to this feature.
Okay, so I still have to understand in a more in a physical setting how that is possible, except in this model.
Yeah.
But
yeah, I think what you can do, like if we can consider instead of the black hole, let's think about like an SYK system, like the holographic dual of that is some SYK system. And instead of considering an SYK system with like all energies, we just truncate to like some band of energies for the SYK system and look at the thermal state restricted to that band. But this is some band that I can impose, like I impose some IR cutoff and UV cutoff on this thing and allow it to radiate into this other auxiliary system, which has some other separate spin system, which has some rank. And the only thing that's important here is like the rank and entropy are disentangled from each other. Like
I just don't still understand how can you choose the rank of the radiating of the reservoir independently. That's something. Maybe we can continue with the discussion. If we can, maybe we can first finish the talk if you want.
Okay.
It's because this probably requires some discussion that we can continue.
Sure. Okay. Good. So I'm not sure if, so let me just say more generally, like how we understand this mechanism as coming from approximate QEC, which is whenever we look at any quantum information quantity, we would like to understand if they're robust to small errors, since approximate QEC can lead to some small errors, which are not necessarily always under our control. The entanglement entropy is one such quantity, which has a nice continuity bound, which was proved by Fans and Ordinard, which basically says that if you change the state a little bit, the entanglement entropy doesn't change too much. There's a similar thing that we proved in this paper with Chris about reflected entropy, where if you just change the state a little bit, the reflected entropy doesn't change too much. But on the other hand, the important point is that the relative entropy is not like that. The relative entropy is actually very discontinuous since it's sensitive to small eigenvalues. The one simple, very, very dumb example to see this is if you have two density matrices of this form. So this one has a 0, and this one, instead of a 0, has an epsilon. Then these two states are very close to each other. If you compute the operator distance between these two density matrices, they're order epsilon. But when you look at the logs of these density matrices, which are the modular Hamiltonians, then these are really far from each other because the log acting on this makes it infinite. And whereas here it's finite. So the log is very sensitive to these small eigenvalues, and hence the relative entropy is also sensitive to these small eigenvalues. This was the general mechanism because of which we saw these errors. What we saw in this previous example was in the microcanonical ensemble, we didn't see such effects. There were 0 eigenvalues, and we found that JLMS was perfectly consistent and so on. And we found only non-perturbatively small errors. But there's a very small distance between the canonical ensemble and the microcanonical ensemble. They're very closely related. But and since the entanglement entropy has a continuity bound, the entanglement entropy doesn't change much whether you compute in the canonical ensemble or the microcanonical ensemble. But the relative entropy was very sensitive to this, and it sees this feature. So that is the general mechanism because of which we're seeing these corrections to quantum JLMS. And this is something that we should always be careful about. Essentially because there's no continuity bound for the relative entropy when you have small eigenvalues. So that's sort of the punchline. which is we can engineer arbitrarily large corrections to this quantum JLMS formula, which essentially come from non-perturbative errors in quantum error correction because of this approximate nature of quantum error correction. And the Euclidean version of that was, we saw that there were these replica symmetry breaking contributions to the path integral. And the essential reason why there are these arbitrarily large violations is because there was no continuity bound to protect from large violations under these small errors. So this is sort of the take-home message from our work. I'd just like to briefly mention the implications of this. As I said before, there was an operator version of JLMS, which was related to the modular Hamiltonian. Again, that's also violated because the log is again sensitive to such small eigenvalues. On the other hand, there have been other, so for example, when you compute rho log rho, it's not sensitive to these small eigenvalues because even though there's a log rho, there's also a rho that makes those errors smaller. And similarly, people have considered modular flow acting on the same state, and those are robust to such corrections for the same reason, where if you act log rho on the state rho itself, then it's robust to such errors. But if you consider any other state, then there can be these effects coming from this discontinuity. One thing that I had said earlier, which was that JLMS allows you to guarantee that there's a operator reconstruction that's allowed. This is unaffected because JLMS only proves a lower bound on operator reconstruction. And so it's a sufficient but not necessary condition. And in fact, in this particular example that we talked about, you can actually show that it's still fine. You can still use the PETS map to reconstruct the interior. And that doesn't have large corrections because that's sort of a more continuous like property, whereas the relative entropy has large corrections. One would, I mean, as was suggested, one would like to have more realistic models where one can come up with such examples and have more control. But I mean, the gravitational path integral is a little less under control when we talk about higher dimensions. There's all sorts of subtleties. So these two-dimensional models at least help keep track of those effects. And the important thing is that, I mean, the idea is that many of these things should be universal. And if one could argue that these things are universal, then at least tractable models indicate what happens more generally. But more generally, I think there's another way to approach this problem. Instead of the Euclidean path integral, we should think about quantum error correction directly and think about continuity bounds on these quantum information quantities. So for certain quantities, we know that they're continuous under these small deformations. And so we don't need to worry about errors in approximate quantum error correction. But maybe in other situations, they're not. And those quantities we should be more careful about. So with that, I'd like to thank you for listening.
Thanks, Pratik, for this nice talk, and time for questions. Okay, maybe we can continue offline.
Okay.
Because,